Welcome to Brain Vision.
Hi there. So in this problem, let's write down what we know. So we know at a certain time, length L equals 1, and W and H are both 2. We also know that the length and the width, L and W, are increasing at a rate of 2 meters per second. So in other words, dL dt equals 2. dW, dt also equals 2. And h, the height, is decreasing at a rate of 3 per second. So that means dH dt is negative 3. Okay, so that's all the information that we have. And we're supposed to find the rates at which three quantities are changing. So for part A, it's the volume. So for part A, we want to find dV dt. Okay, well, to do that, let's remember the formula for volume. So the volume of the box is just length times width times height. So L times W times H. Okay. And in order to get our dV dt, let's follow the chain rule. So the chain rule says we will need the partial of d, or partial of v with respect to L, right, times dL dt plus partial of v with respect to W times dW dt plus partial of v with respect to H times dH dt. Okay. So these will be pretty quick. The derivative of partial of v with respect to L, again, we're just going to look up here for all these partials. If L is considered to be the variable, then the derivative is just W times H. And we know dL dt is 2. Partial of v with respect to W, again, just looking up here, it'll be L times H. And dW dt is also 2. Finally, partial of v with respect to H is L times W, and dH dt was given to us as minus 3. Now just putting in our values for W and H and L, we'll get our answer. So let's see, W and H are both 2. 2 times 2 times 2 is 8. L and H, 1 times 2 is 2, times 2 is 4. L times W, 1 times 2 is 2, times negative 3 is negative 6. 8 plus 4 is 12, minus 6 is 6. And we should get our units correct, so everything is in meters and seconds. Volume is measured in cubic meters, of course. So 6 cubic meters per second, it's increasing at that rate. So that's the answer for part A. Okay, so for part B, we will do much the same thing. Let's have to erase this here. But this time, instead of volume, we want how quickly the surface area is changing. So as before, we will have to begin with a formula for surface area. Good, so let's change this. So now we want, we'll use A for area, we want dA dt. Okay, and the surface area of a box or rectangular prism is, well, we can think of it, but it's going to be 2 times, and then just think about there are 6 faces to the box, but really there's just 2 copies of each of the 3 different possible pairs, right? So the base is like LW, and then one of the walls would be, say, WH, and the other wall would be, which one haven't we done yet? LH. So that's surface area. And we'll do the exact same thing to get dA dt. We're just going to need partial of A with respect to L times dL dt. Plus partial of A with respect to W times dW dt, plus partial of A with respect to H times dH dt. Okay. For the partials, we'll have to look at our formula for surface area up here. So with respect to L, this first term here will give us a derivative of 2W. Okay, and this term here will give us a derivative of 2H. dL dt, again, is given to us as 2. With respect to W, this will feel much the same. First term gives us a derivative of 2L. Second term gives us a derivative of 2H. Third term is 0, since there's no W in it. dW dt is given to us as 2. And finally, partial of A with respect to H. Let's see, nothing in the first term. We get 2W from the second term, and we get 2L from the third term, all times dH dt, which is -3. So now plugging in our current values, W and H are both 2. 4 plus 4 is 8 times 2. That should give us 16 from the first term. L is 1, H is 2. So we got 2 plus 4 is 6. Times 2 is 12. And for this third one, W is 2, so that's 4. L is 1, that's 6 again, times -3 is -18. So 16 plus 12 is 28. 28 minus 18 is 10. And this time our units, since they're area, our units will be square meters per second. So that's our answer for B. Okay, we'll erase this. And now finally, we're going to do the exact same thing for part C, except this time instead of volume or area, we're going to be calculating how quickly the length of the diagonal is changing. So this is a little more interesting. So this is part C. And let's just call that diagonal capital D, so we remember what it is. So we're going to want how quickly is the diagonal changing with respect to time. Okay. There's several ways to think of this. Hopefully, if you think about maybe if you've done any vector calculus already, or think about three-dimensional distance between 3 points, really this is just, it should feel like the Pythagorean theorem. So the diagonal is from one corner of the box to the opposite corner, or whatever this distance is. And the formula for that, again, this is just like a three-dimensional version of the Pythagorean theorem. It is square root of L squared plus W squared plus H squared. Just right, so just as the diagonal of a rectangle would have been the square root of the length plus width squared. So we just add one more dimension here. So that's the formula for the diagonal of a box. Okay, which as always for calculus, we'll think of this as 1/2 power to make our derivatives easier. Okay, and so for the last time, d dt will equal, well, we're going to need the partial of d with respect to L times dL dt plus partial of d with respect to W times dW dt plus partial of d with respect to H times dh dt. Okay. Partial of d with respect to w, or with respect to L. And the good news is once we calculate this, it's going to be the same for the other two variables, just because everything is symmetrical in this formula. So off we go. We'll get this. So we have, well, it's going to be 1/2 times everything in there still. Power rule. So this has been pure power rule so far. Now, so we'll have to be a little careful. Chain rule tells us we need to multiply this by the derivative of that quantity inside. Now that derivative with respect to L, if L is our only variable, we just get 2 times L. So that is a partial of d with respect to L. And now for dl dt, and that's given to us earlier in the problem, that's 2. Good. So again, the good news is we can do the exact same thing for w. The derivative will look the same. It'll be 1/2 L squared plus W squared plus H squared, and then minus 1/2. But this time times 2W. And dw dt was given as 2. And same thing over here, 1/2 L squared plus W squared plus H squared to the minus 1/2 times 2H this time. And dH dt is given to us as -3. Okay, now just time to plug in our values. So let's see, L squared plus W squared plus H squared. L is 1, W is 2, H is 2. So if we square all these, we'll get 1 plus 4 plus 4, which is 9. Right, so, and then thinking how this -1/2 power works, that's the same thing as a square root on the bottom. So this entire part becomes, right in the parentheses, this all becomes 1 over the square root of 9, which of course will be 3 in the next step. This 1/2 and that 2 cancel out, so we just get L times 2. But L is 1, so we get, everything is just times 2. So when everything's done, we should get 2 over the square root of 9, which of course will be 2/3 at the end. Over here, let's see what we get. Well, again, the good news is every time we do this, we're going to get the same thing. We just did this calculation. So this is 1 over the square root of 9. Again, this 1/2 and that 2 will cancel out. All we'll be left is with is W times 2, and W is 2. So 2 times 2 will give us, let's see, 4 on top. And finally, once again, this part we know already gives us 1 over the square root of 9. The 1/2 and the 2 cancel. We're left with H times -3, but H is 2. So 2 times -3 is -6. So we're left with 2/3 plus 4/3 minus 6/3. But if we look at the numerators, since the denominators are all the same, 2 plus 4 is 6, minus 6 is 0. So after all that, we end up with a final answer of 0. And we should think of our units. This is the length of the diagonal, so this is just meters. And our time is seconds. So 0 meters per second. In other words, at this moment, given the info we have, even though all the sides are changing lengths, that diagonal at this moment is actually staying constant. It's not growing or shrinking. Hopefully that helped.